Hi, grade 9s. So we've been looking at linear relations and what that means and the difference between independent and dependent variables. And now we want to go on to this next learning goal, which is about key features of linear relations. So here we have the learning goal connecting key features. I'm going to talk about what that means, key features of linear relations, to a table of values. So we're still working with these three ways of representing linear relations: a table of values, a graph, or an equation. So this is what we mean by key features of linear relations. So we've already talked about two of the key features, those being the dependent and independent variables. But there are some more key features we want to talk about. And in this video, we're going to focus in on the initial value of a linear relation, which is the starting value of the dependent variable when the independent variable is 0. So some relations have a starting value when the independent variable is 0, the dependent variable is not 0. And those kind of relations are referred to as partial variations, and we'll get into that in a moment. So the initial value is one part. The other part is the rate of change. So when we have variables that change, in our case in a linear fashion, the rate of change, or growth rate, we sometimes call it growth rate, and from a graph we often refer to this as the slope of the graph. But if you think of the rate of change as the change in the dependent variable when the independent variable changes by just 1 unit. So we have to be careful about this part of the definition. It's the change in the dependent variable when the independent variable changes just by 1 unit. So in a table of values, for example, the independent variable is often changing by more than 1 unit, in which case we have to figure out what the rate of change is for just 1 unit. There are some more key features that we're going to address in another video, but that's it for now. So let's have a look at an example. So here in my example, I've got a graph here, and my graph has, of course, the independent variable on the horizontal axis and the dependent variable on the vertical axis. This graph starts at the origin, or 0, 0, 0 on both axes, and this blue line here, where the initial value is 0, is an example of what we call a direct variation, or sometimes called a proportional relationship. If the initial value is not 0, as in this case here, the graph starts up here on the vertical axis when the independent variable is 0. This does not have an initial value of 0, so we call it the partial variation. It means part changing and part staying the same. On a line, the initial value is, of course, here where the line joins with the vertical axis when the independent variable is 0, and the growth rate or rate of change is found by how much does the line go up when the line goes 1 unit across. So the independent variable is increasing by 1. How much does the dependent variable change? From a table of values, this is what I was talking about just a little while ago. In this case, the independent variable is increasing by 2. So every time it does that, the dependent variable increases, in this case, in this example, by 20. So the growth rate is not 20. It increases by 20 for every 2 increases in the independent variable, so the rate of change is 20 divided by 2, or 10. And the initial value here is 30 when the independent variable is 0. The dependent variable is 30, so that would be the initial value. From an equation, so here we've got an equation here, and we're going to come back to this equation in a later video, or this example in a later video, but for now, we always have the dependent variable, which is usually just a single letter. I've used dv here to represent dependent variable, but normally we just have one letter here. On the left hand side, the independent variable is over here, and then the number in front of the independent variable, the coefficient of the independent variable, is the rate of change, or growth rate, and then the starting value is here at the end as a constant. Noting that the starting value could be positive or negative. Negative if it's below the horizontal axis, or positive if it's above. So that's how we would show that in an equation. So we're focusing in on rates of change and starting values, and we're also looking at the difference between partial and direct variations. So this was a ticket that we used, that I gave, and the idea was that you had to use the data that was given, or the information that was given, to generate a table of values. As you can see here, there's a table of values for each of these. These are computer companies. And then from there, write an equation, and from there, draw a graph, and then answer some questions about direct variations or indirect variations or partial variations. So the information was given on the ticket and talked about Compufix being a company that has a base fee or a set fee of $50 and then an amount per hour of $30. And then Computer Doctor over here had no base fee, but they charge $55 per hour. So completing the table you just use from the description. So for Compufix, if there's no hours, the cost would be still $50. Not that you would actually hire a company to do no hours of work, but that's what it would be. And then for each extra hour, $30 more. And for Computer Doctor, nothing as a set fee, but $55 each hour. So the way we'd write that in an equation, and I really should define what these variables are. In this case, we're using T for time, C for cost, remembering that the dependent variable, which is cost in this example, goes on the left of the equation, the independent variable on the right. And then this 30 here is showing us the growth rate, so it increases by $30 each hour, and the 50 at the end is the initial value. There's no initial value over here, $55 per hour, the growth rate is here. So if we were to graph these, just a couple of things with regards to the graphs that I wanted to point out. First of all, you should put the name of the variable with the units in brackets like this on each axis, time in hours, cost in dollars. You have to make sure that your scale is uniform. So you can see here that starting at 0, I've gone up by 1 square for every 20 on the vertical axis and 2 squares for every 1 on the horizontal axis. And you have to make sure you've got the same values between each number on your axis, otherwise it's not linear and it won't look right. Same thing for this one. I did not start my my line at the first data point because my assumption was that if you didn't hire the company for any hours, then you wouldn't actually pay them anything. You hadn't actually hired them. So really it starts off at 1. And I've used dotted lines for my graphs to show that, with the assumption that the companies only charge for complete hours. So they're either going to charge you for 1 hour, 2 hours, 3 hours, nothing in between. But if you think that the companies would charge you an amount for a part hour, then you would join these points together with a solid line. And finally, I've put arrows at the end here to show that these graphs would continue past the time available. There were some questions asked about this on this ticket about which of these two companies would you hire if you were only going to use a small amount of time, or which one would you hire if you were going to use a larger amount of time. And so we can see either from the table, from the equation, or just by looking at the growth rate. The one with the higher growth rate is Computer Doctor. They charge $55 per hour compared to Compufix for $30 an hour. But if the number of hours was really small, like let's say you only wanted to hire them for 1 hour, you can see that Compufix is more expensive than Computer Doctor because of that flat fee of $50. But once you get past a few hours, the Computer Doctor ends up being more expensive because of the hourly rate. So you can see that the point at which they're both the same is 2 hours. So after 2 hours, both of them cost the same amount. But anything less than 2 hours, Compufix is more expensive, and above 2 hours, then Computer Doctor is more expensive. So that's kind of where we're going with these. Initial values and rates of change are important because they help us make decisions about things. So then we completed an activity sheet where we looked at these graphs initially, and we said, what can we see from these graphs? What are the similarities and what are the differences between the graphs? And so you can see just by looking at them that the pairs of graphs are different. The two on the left in A over here, they start at the same point but they don't end at the same point. They have different growth rates. That's the main difference between them. In this case, these two lines have the same slope, so they have the same growth rate, but they start at different initial values here. So that was the main difference between these two. So I gave you some time to think about that. What are the similarities and differences? And then we talked about it together. So this is a summary of what we came up with together. We said that in the first graph there were several similarities that were mentioned. They are both partial variations. They both start above the zero on the vertical axis here, as you can see. So they're both partial variations. They have the same initial value of $200, and both show continuous data. These are solid lines, so the data is continuous. The main difference was that they have different growth rates, as already mentioned. And there was another difference that was mentioned, is that one is always more expensive. So the upper one of the two is always more expensive, no matter what the number is on the horizontal axis. For the second set of graphs, the similarities were that, again, they're both continuous. They have the same growth rate, and there were two ways of saying this. One person said they had the same growth rate, the other person said the lines were parallel, which kind of mean the same thing. But they do have different initial values. One starts at 100 and one starts at 200. So those are the main differences there. And then after that, we worked on some more of that same activity sheet, and I did this consolidation at the end. You were asked to compare 4 different formulas for determining salary, and these 4 formulas are shown here on the screen. And you can see that the 4 formulas, they both have the same variables, cost and number of hours. So they both have the C and the H in them. All 4 equations have those, but they have different growth rates. The growth rate is the coefficient of the independent variable. So $5 per hour here, $10 per hour here, $30 per hour here, and $35 per hour here. And they all have different initial values, $30 here, 35, 10, and 5. And so you are asked questions like, if this was being used to calculate your salary, which of the equations would you most like to have if you worked for a small number of hours or if you worked for a large number of hours? So if you're working for a very small number of hours, and there was a question which would be the best, which would give you the highest amount if you only worked for 1 hour. And if you only worked for 1 hour, it turns out that the second equation here was the best. It gave you $45, and even though the hourly rate is only $10 per hour here, you do get this base amount of $35, which makes it the highest if you only work for 1 hour. But once you're working for a few hours, this flat fee doesn't really amount to much, and then you really want the one with the highest hourly rate or the highest growth rate. So it was this equation over here, $35 per hour. So in summary, sometimes it's best to have a high initial value if the number of hours is small. Sometimes it's best to have a high growth rate if the number of hours is large. So we wanted to compare those things. The growth rate and the initial value both have an impact when making decisions related to linear relations. So that wasn't the whole activity sheet, but that was the main idea of it. And then you had some additional work to complete for MSIP or homework.